Good morning and welcome back. Today we will talk about relativistic mechanics. Some people will curious about we are talking about electrodynamics, but now we will talk about mechanics. Why? The reason we talk about mechanics because we will introduce some idea and which those ideas can be used to electrodynamics, both mechanics and electrodynamics. That's why we will study mechanics, relativistic mechanics. We will talk about three important terms. First is conservation, and then is invariance and covariance. Three ideas. Please allow me to explain three ideas in more detail. First, the conservation. Conservation, we talk about conservation of energy, conservation of momentum. Yes, these terms are conserved quantity. So, a conservation of a quantity means that it remains unchanged in time in a given Lorentz frame. For example, collision before and after, before and after, unchanged in time in a given, just a given Lorentz frame, a given inertial frame. For example, the relativistic momentum and energy of an isolated system of particles are both conserved after a collision. This is a fundamental law to be discussed in this section. So conservation law is the fundamental, very important. So conservation of energy, conservation of momentum. Next one is invariance. Invariance of a quantity means that it is invariant in value under a Lorentz transformation. For example, we have two Lorentz frames. One is at rest. The other is moving at a constant velocity to a certain direction. Then, in these two frames, the quantity is the same. That is invariant quantities. Such a quantity is called a Lorentz invariant or Lorentz scalar. Remember, in the last week, we just talked about some inner products is a Lorentz invariant independent of the coordinates. Now we will use those properties. Maybe we should go back to for example, the dot product of two 4 vectors. In this coordinate, in another coordinate, always the same, always the same. What else? Divergence A, the same, in this coordinate and in this coordinate. That is invariant. Okay. 27. So an invariant quantity which means it do not change in a Lorentz transformation under a Lorentz transformation. An example will be provided in these sections. Third, the term covariance refers to the physical law A physical law is covariant if it is invariant in form under the Lorentz transformation. Invariant in form under the Lorentz transformation. Remember, for special relativity, we have two postulates. The first postulate is, remember, maybe we should go back to page 1, skip, and go back to page 1 or page 2. We have the principle of relativity. The principle of relativity, all physical laws has the same form in all Lorentz frames. That is, their form should be the same. They should be covariance. Okay, come back to 27. 27. Okay, so we will talk about 3 conditions. Let me explain. A physical law is covariance if it is invariant in form under the Lorentz transformation. As will be shown, the new laws of relativistic mechanics, and the existing law of electrodynamics, electromagnetism are all covariant. That is, the Maxwell equation are covariant, and the relativistic mechanics are also covariant if we write into the new laws, new expressions. Okay, I will show you the mechanics will be covariant and electrodynamics covariance. Maxwell equation, conservation of charge. Conservation of charge should be conserved. Charge should be a conserved quantity, and it should be covariant, conservation of charge. I will show you step by step. And after that, I will give you 2 examples. Okay. First, the 4 momentums. Momentum has 3 components, but we know if we can have another components, then we can form a 4 vectors, a 4 vector. Okay, that's the different expressions. As shown in A.20a, A is appendix A, equation 20a. If we define the momentum of a particle as this form, gamma mv, and energy as this form, E defined it as gamma mc squared. M is the rest mass. Then the 4 momentum is E over c. Gamma dimension is m is the rest mass. C squared divided by c. So c is the speed of light, and v is the speed of the particle. So they have the same dimension. We have 4 quantities. Here we use x, y, z, and e. X prime, y prime, z prime, and e prime. Okay. In the previous case, we use e, this one, ps, py, pz. Okay. Slightly different. So in the new coordinates, they can transform under the Lorentz transformation. Maybe I should write into x, y, pz, and e. Okay, remember I mentioned that we have 2 expressions. One is x, y, z, and e. First component, second component, third component, and the 4th component. If we can change here, e to here, like this one. Zeroth component, 1, 2, 3, two expressions. Some textbook use this expression, some use this one. Okay, it doesn't matter. Use this one, the relative motion is in the S direction. Use this one, the relative motion is in the Z directions. Okay, different expression, but same physics. 1, 2, 3, 4, 0, 1, 2, 3. In Appendix A, we first define P as this form, E as this form. Then show that the law of conservation of momentum and energy is covariance. Okay. That is conservation of energy and momentum. Conserve and should be covariant. That means they should be the same in all Lorentz frames, the same invariant in form. Conversely, from the requirement of the covariance of this conservation law, we can define the definition of P as this one and E as this one. So you can start from this definition and obtain this one, or start from here and obtain this one. Okay. Move on to the next page. Now, we have a 4 vector, but remember the inner product or a dot product of 2 4 vector is a Lorentz scalar. So we have P dot P. This symbol means momentum 4 vector. Momentum 4 vector, another frame. So after the inner product, we got P squared minus E squared over C squared. And that's in one Lorentz frame, one inertial frame, in another inertial frame. That means E squared minus P squared C squared is a Lorentz scalar. Invariant quantity. Not momentum and energy are conserved quantity. But interestingly, E squared minus P squared C squared, P is the momentum, absolute value of momentum. C is the speed of light. E is the energy of the particle. Okay, including the rest energy. Gamma mc squared. In frame K prime, if the frame K prime is the rest frame of the particle, K prime is the rest frame, particle do not move, and energy equals rest mass energy. And so P prime is equals to 0, 0, 0, mc squared over C, so mc, and P squared equals P prime dot P. So another frame always give us this value. So we can estimate E squared minus P squared C squared just equals to minus M squared C squared. On the other hand, we can exchange C squared to here, C squared to here, and switch, change sign. So we got E squared minus P squared C squared equals M squared C squared. That means this is invariant, and Lorentz M rest mass is invariant. Rest mass is a Lorentz invariant. Oh, that's new. We do not expect that, but the truth is the rest mass should be a Lorentz invariant. That means in all the coordinates, rest mass should be the same. Rest mass should be the same. Rest mass should be the same, but energy is not the same. For example, in rest frame, energy is here, and in other frame, energy is another one, gamma mc squared. So energy is not the same. So energy is not an invariant quantity. Momentum, of course, not the same, not an invariant quantity. But energy minus momentum squared times c squared is an invariant quantities. Okay, energy and momentum are conserved quantity. Before collision, after collision, they are the same, but they are not invariant quantities. And energy minus momentum squared c squared is an invariant quantities. Okay, so the rest mass is invariant. Okay, this has in fact been assumed in section 2 of appendix A, where we define the Lorentz transformation equations for P and E, and 23 is a useful formula for its related particles, total energy E and momentum P. Momentum in particle physics is often expressed as GeV over c in particle physics. GeV over c. GeV is the energy over c. For a relativistic particle, we can still speak of its kinetic energy. Now, its kinetic energy is defined as E minus mc squared. Mc squared is constant, is rest mass energy. So the extra energy is kinetic energy. Gamma minus 1 mc squared. Gamma is 1 over square root 1 minus v squared over c squared. So when gamma is velocity is small, when the velocity is small, distance equals to 1 over 2 mv squared. That's the classical definition of kinetic energy. So traditionally, momentum equals mv. That's the classical non-relativistic definition. Relativistic definition, we need to add a gamma here. That's the relativistic definition. Okay. That will be much more convenient. Compare with the P equals mv, E, or kinetic energy equals 1 over 2 mv squared. That's valid for low velocity. Okay. Now, we just consider a system of one particle. If we consider a system of many particles, not just one, what should we do? We should consider a system of particles, each with 4 momentum, 4 vector, 1, 2, 3, 4. J runs from 1 to total number of particles. Since the Lorentz transformation is a linear transformation, that is the sum of any number of 4 vector also obeys the Lorentz transformation. Okay, that is if we have 2 coordinates. One is frame K, just this one. the other is another frame. Because Lorentz transformation is simple, it's a linear transformation. So sum over all the value, and after the summation and before the summation, they follow the same transformation matrix. So before and after should be the same. So therefore, P dot P equals sum over all P is a Lorentz invariant, just like the previous case. This is a generalized case. Generalized. That is valid for a system of one particle, two particle, a system of many particles. The same. This equation is still correct. Okay, so we just talk about the first equations. For momentum, invariant quantities. The law of conservation of momentum and energy. Let's have a look at the conservation. We just talk about invariant. In relativity, the conservation of momentum and energies comes in one law. Simplify. Conservation of momentum and conservation of energy can be simplified to one law, not two, but just one. Conservation of energy, conservation of momentum. The law states that for an isolated system of particles, for momentum before collision and for momentum after collision should be the same for a given reference frame. That is, which implies that sum over pxj, sum over j, px, py, pz, and energy of each particles should be conserved. So we have two expressions. One is before collision, before interaction, or after interaction. So we can write into this form. Since the conservation law is expressed as a four-vector relations, it has the same form in all Lorentz frame. The same form. So conservation law should be very easy and always in the same form. Okay, pretty good, pretty convenient. Okay, and P is a conserved quantity. The dot product of P must be conserved. P dot P. P dot P should be this one. Sum over P dot sum over Pj minus this one. So before collision and after collision, they should be the same. So let's discuss. P dot P for an isolated system is both invariant, Lorentz invariant, and conserved quantity. Conserved quantity do not change, and invariant quantity. So P dot P is invariant, is conserved, and always maintain the same form, covariance. Okay, so P dot P is pretty good. Invariant, conserved, and covariant. Okay. However, if the system is not isolated, which means the particle will interact with the outside, it's still a Lorentz invariant, but no longer a conserved quantity because it will exchange the quantity with the surrounding. And P before collision, P after collision is a fundamental law. That's the conservation of energy and momentum. It's not a derived relation, it's a fundamental. from observation. No exception at all, at least for now, in which non-relativistic law of conservation of momentum has been extended to include the energy E equals gamma mc squared. That's a very important aspect of this law, is that it applies to all processes in an isolated system, such as elastic and inelastic collisions, nuclear reactions. Yes, this law can be applied even for the nuclear reactions. Particle decay. One particle decay into another particle and radiate to energy. This is still correct. As a result, the total rest mass of the system may not be conserved, as is illustrated in the following two problems. So we will show you this one is a conserved quantity, but the total rest mass of the system may not be conserved quantity. And P dot P is correct. It's invariant. Okay? Let me show you two problems. First, problem 1. If we have two identical particles, exactly the same particles of rest mass m, equal and opposite velocity, one move to the right, the other move to the left. And because of the velocity, we can calculate the gamma factor, Lorentz factor, the gamma factor. This is before collisions. After collisions, these two particles combine into one, collide head-on inelastically. Because they are inelastically, if they collide elastically, they will become doing, 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 doing. However, they collide head-on inelastically to form a single particle. Find the mass and the velocity of the new particles. How to do that? Momentum before and after conserved. So the collisions occurs in the center of momentum frame. That's the center of momentum frame. That is the frame in which the sum of the momentum of all particles vanish. Center of momentum frame, Cm, denoted at Cm. For later comparison with the result in problem 2, we denote the mass of the new particle by mcm to indicate it is created in the center of momentum frame. Conservation of momentum. The new particle is stationary. Before, momentum 0. After, 0. Yes, good. Conservation of energy. Before, gamma mc squared. Gamma mc squared. After, we have capital M, Cm, center of momentum frame. C squared cancel, 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 cancel. So eventually, the center of mass becomes this one. Okay, pretty good. In this problem, we found that after the collision in elastic collisions, the rest mass changed from m 2m to 2 gamma m. The rest mass has been created from the kinetic energy gamma minus 1 mc squared kinetic energy of the collision particles. There is no need to know where is the inside, what's inside the new particle. We only need to know is its rest mass and hence the energy associated with it. Okay, we don't need to know the interior structures, but we know its energy. We know its rest mass. Yes, it will become hotter. A hot object has a red mass greater than when it is cold. That's an interesting idea. We normally consider the particle to be the rest mass to be independent of the temperature, but actually it's not. After collision, you can expect the temperature inside should be hot. The difference in the rest mass due to an increase in temperature can in principle be measured by its acceleration due to a known force. We know that at least one of the added mass is in the form of thermal energy. So thermal energy plays a role just like energy. It's a form of energy. In many other cases, it's not possible to know what's inside. Okay. Nuclear fusion and fission. Fusion and fission. 融合分裂 reactions are example of non-conservation of rest mass. Therefore, the rest mass is not conserved. So you might confused. You might have the wrong impression. Let's go back. In this case, you will think before in different coordinates, this is an invariant quantities. M is Lorentz invariant. That is, if we do not, it's invariant if we have particle here and we have do not combine into one, then it's invariant. For example, we have a particle at rest. Its rest mass is m. Another observer is moving at velocity v to the right. Okay, then he or she see this particle move to the left, but the rest mass is the same. Yeah, in this case, it's invariant. However, let's go back to here. Here, they combine into one. That's the rest mass. However, in this one, after collision, after inelastic collisions, the rest mass changed to m cm and is greater than the original two particles. Much greater. That depends on the energy. Depends on the velocity. In fact, all reactions, chemical or nuclear reactions, the energy is absorbed or released involve a corresponding change of the reactant's total rest mass. Okay. Problem 2. Let's consider another conditions. Another condition, we have a particle, once again, move to the right, rest mass m, but this time we have another particle fixed initially, and they collide and combine into one. So after collisions, the particle move to the right because conservation of momentum tells us before gamma mv, after gamma st, mst, vst. Okay, what is st? St means stationary target frame. A particle of rest mass m and velocity v collides with a stationary particle of the same rest mass and is absorbed by it, becomes one. Find the rest mass and velocity of the new particle. The collision occurs in a stationary target frames. Stationary, fixed target. This one is fixed. So we call stationary target frame. In the previous problem, center of mass frame, CM, So we denote the new particle mass by mst and velocity by vst, Lorentz factor by gamma. Okay, here, the same. M, gamma, V are also stationary target frames quantity. So conservation of momentum tells us that. This one easy. Conservation of energy tells us that gamma mc squared plus mc squared equals gamma st mst c squared. So we have two unknown, one, two equations. We can determine VST. Oh, sorry. We can determine everything. So VST equals gamma plus 1 times V. MST unknown, known. Okay. So the only two unknown is 1, 2. So 1 over 2 give us VST cancel equals to this one. Gamma V times gamma plus 1. Okay, divided by gamma plus 1. So substitute this one into here. We got MST actually into 1, not into 2. 1 tells us that. MST equals to this one. Gamma cancel with this gamma. So we have gamma plus 1, gamma st. Okay, so we have two unknown, MST, VST. Once we got VST, we got gamma st. Okay, we got VST, we got gamma st. So MST squared equals M squared, gamma plus 1 squared, gamma st squared. But gamma st squared equals to this one. Okay, we can rewrite this one because we know VST equals to this one. Oh, so after simple algebra, gamma squared plus 2 gamma plus 1 minus this one. Okay, cancel. So eventually we got two terms. Gamma plus 1 squared minus gamma squared V squared over C squared. That's this one. And this one can be further simplified Just factor out gamma squared. We got 1 minus v squared over c squared. And this is 1. 1 plus 2 gamma plus 1. So eventually, we got mst squared equals 2m squared gamma plus 1. So mst equals this one. Quite different from the previous case. Let's compare. Okay, we still have 2 pages to go. Let's compare. In problem 1, we consider center of mass frame. The new particle's mass is mcm equals 2 gamma m. In problem 2, the new particle's mass is mst equals square root 2 1 plus gamma times m. Gamma is the Lorentz factor. Condition 1, center of mass frame, stationary target frame. Okay? Gamma is the Lorentz factor of the particles before collisions. Before collisions. In particle physics experiment, mcm c squared or mst c squared is the energy available for the creation of the new particles. Why not for this one? Let's mc squared, that's for rest mass. Okay. The rest energy of the electrons or positron is mc squared equals 0.5 MeV. If 2 eV of energy is indeed for the particle creation, we want to create a particle of very high energy, rest mass, then we need much more energy for this one. For example, if we want to create a mass of this one, we need a gamma value very, very high. But if we use stationary target frames, we need extremely high because some of the energy is lost. Okay, lost to this one. Okay, so in this case, the gamma is 1.9 times 10 to the 6. This one is 7.66 times to the 10 to the 12. Very high. The energy associated with gamma is to be obtained in an accelerator. So to create a particle of 2 TeV, we need head-on collisions. 2 particles collide head-on. That's the comparison. Kinetic energy needed in the center of mass frame and kinetic energy needed for stationary target frames. Rest energy is already in the particles, so we can only increase the kinetic energy. Therefore, if we use colliders collide head-on, we need a much lower energy. This shows that the far less kinetic energy is needed in the center of mass frame than the stationary target frames. In fact, all the kinetic energy of the 2 colliding particles is put in use in the center of mass frames, while in the stationary target frames, 99.99995% of the kinetic energy of the incident particle is waste. That's why it wastes a lot of kinetic energy. That's why it needs much more energy. That's why the International Linear Collider project plans International Linear Collider Project plans to accelerate both electron and positron to energy positron to energies up to 1 TeV 正负电子对撞机正电子负电子对撞机 so that the collision occur in the center of mass frame. Why use a long linear accelerator instead of a more compact circular accelerator? We will talk about this issue in chapter 14. Okay. We have a pretty good idea about relativistic mechanics. Next time, we will talk about covariance of electrodynamics. Okay, I will stop here. See you next time.